The 1CD FTV is a 2-liter inline 4-cylinder DOHC 16-valve diesel engine with common rail injection system and turbocharger. The engine has adopted numerous cutting-edge technologies. Among them, this video describes the new diesel injection system, which has achieved high performance, clean emissions, low noise, and low vibration. The common rail injection system accumulates the necessary pressure required for injection of fuel inside the rail. Just like the EFI system of the gasoline engine, this system injects fuel into the cylinders by opening and closing the injectors in accordance with the electrical signals output by the ECU. Therefore, this system can finely regulate the injection volume and timing, thus contributing to highly efficient operation and clean emissions. Furthermore, because this system accumulates constant fuel pressure in the rail, it does not create sudden pressure rises and offers the advantage of quieter operation. Now, let's look at the system. Let's start with the sensors. Here's the accelerator pedal position sensor that detects the opening angle of the accelerator pedal. The airflow meter. The intake air temperature sensor. The turbo pressure sensor. The water temperature sensor. The crankshaft position sensor that detects the rotational angle of the crankshaft. The camshaft position sensor that identifies which cylinder is at TDC. And the fuel pressure sensor at the common rail, which detects the pressure inside the rail. Here are some of the actuators used in this system. The suction control valves, or SCVs, which are located on the supply pump assembly, control the amount of fuel that is fed to the supply pump. The electronic driver unit, or EDU, which boosts the injection signal from the ECU. And the injectors that inject fuel in accordance with the injection signal. The fuel is drawn up from the fuel tank by the feed pump located in the supply pump assembly. Then it passes through the fuel filter and is fed to the supply pump. The fuel becomes pressurized in the supply pump to reach the injection pressure. The pressurized fuel is fed into the common rail where it is accumulated. The fuel that accumulates in the common rail is distributed via the injection pipes to the injectors of the cylinders. Then the injection signal from the ECU opens the injectors to inject fuel. The fuel pressure that is created in the supply pump varies according to driving conditions. It is approximately 20 megapascals at idle and increases to as much as 135 megapascals during high-load, high-speed operation. Let's look at its internal construction. The supply pump contains an inner cam, which is driven by the engine. On the inside of the inner cam, there are two sets of opposing plungers. Each set of opposing plungers is positioned at a 90-degree angle from each other, and each plunger operates independently. The tip of each plunger is provided with rollers that come in contact with the inside of the inner cam. The inside of the inner cam is oval. The rotation of the inner cam pushes the plungers via the rollers, which effectively pumps the fuel. The use of the two opposing plungers in this manner minimizes the drive torque fluctuations, which makes for quieter operation. The fuel that has been sent by the feed pump flows past the suction control valve, or SCV, and the check valve. The fuel is then pressurized by the plungers and flows via the delivery valve and is fed into the common rail. The SCV regulates the volume of fuel that enters the supply pump plungers. During the suction stroke, the longer the SCV remains open, the greater the volume of fuel that enters the pump plungers. And because a large volume of fuel is pumped, the fuel pressure becomes high. During the suction stroke, the shorter the SCV remains open, the smaller the volume of fuel that enters the pump plungers. And because only a small volume of fuel is pumped, the fuel pressure becomes low. In this manner, the ECU controls the opening of the SCV so that an appropriate fuel pressure can be reached. Let's watch on an oscilloscope to see how the SCV is controlled. To easily monitor the operation of the SCV, let's see the electrical current that flows through the SCV. The SCV signal is shown at the top and the fuel pressure sensor signal at the bottom. Here's a comparison between the no-load condition at 1500 RPM and the load condition at 1500 RPM. It's evident that in the load condition, the SCV remains open longer and the pressure in the rail is higher. Thus, according to the signals received from the sensors, such as those of the accelerator pedal or the engine, the ECU controls the SCV in order to regulate the fuel pressure that is needed for the particular driving condition. Then, the resulting pressure is fed back to the ECU by the fuel pressure sensor in the rail. The common rail accumulates the fuel that has been highly pressurized by the supply pump and distributes it via the injection pipes to the injectors of the cylinders. A fuel pressure sensor is provided at one end of the common rail to detect the fuel pressure in the rail and to send it as a signal to the ECU. A pressure limiter is provided at the other end, so that in the event of a system malfunction, if the fuel pressure rises abnormally, the pressure is relieved mechanically. On receiving the signal from the EDU, the injector opens its nozzle to inject the fuel that has been accumulated in the common rail. Let's look at its internal construction. The fuel that is fed from the common rail separately enters the control chamber and the nozzle portion of the injector. In this state, the nozzle is closed because of the pressure of the control chamber and the spring force pushes the needle down. Upon receiving the signal from the EDU, the solenoid valve above the control chamber opens. Then the pressure in the control chamber decreases, which causes the pressure at the nozzle to push the needle upward, and the nozzle opens to inject fuel. A small trimming resistor is installed to each injector to compensate for production variations. The ECU recognizes the resistance and applies correction for injection of each cylinder. How does the ECU determine the injection volume and timing? Let's first look at the injection volume. The ECU calculates the basic injection volume and the maximum injection volume, and whichever is smaller is determined to be the actual injection volume. The basic injection volume is calculated from the engine RPM signal and the accelerator pedal position signal. From these two signals, the injection volume that is required by the driver is calculated. On the other hand, the maximum injection volume is calculated based on the actual intake air volume and temperature that have been obtained from various sensors, such as the fuel temperature sensor, in addition to the engine RPM signal. Thus, a volume of fuel that can theoretically be burned completely is calculated. These two calculated values are compared, and the ECU determines the smaller of the two to be the actual injection volume. In this manner, the ECU is always taking the actual intake air volume into consideration to determine an optimal injection volume that does not generate black smoke. In particular, in the 1CD FTV engine, the changes in the intake air volume during the transient state is detected by the airflow meter in order to correct the injection volume. Now, let's take a look at the injection timing. The injection timing is determined with the basic injection timing that is calculated based on the engine RPM signal and the accelerator pedal position signal, to which corrections are made. For the intake manifold pressure signal, and the water temperature sensor signal. Now, let's take a look at the pilot injection. A pilot injection is a small amount of fuel that is injected before the main injection. Accordingly, when the main injection starts, the fuel that was injected beforehand is already burning and serves to smoothly ignite the fuel of the main injection. As a result, a sudden rise in the cylinder pressure during the combustion stroke is restrained, thus enhancing the quieter operation of the engine. Let's take a look at the actual injector signals on an oscilloscope. To easily monitor the operation here also, let's see the electrical current that flows through the injector. It is evident that the pilot injection takes place before the main injection. To enable the ECU to correctly determine the rotation position of the supply pump, the marks on the pulleys must be aligned while installing the timing belt. The pressure of the fuel becomes extremely high in the common rail. Therefore, pay close attention when installing the unions of the injection pipes or the inlet pipes. If any operation that causes the contact of the union to change, such as the replacement of parts, make sure to replace the pipe. For details, refer to the repair manual. After tightening a union, make sure to check for leaks with the fuel pressure raised. The fuel pressure can be raised by conducting an active test using a handheld tester. In addition, one of the active tests that can be performed is the power balance test, in which the injection to the cylinders is cut off one cylinder at a time. The pressure limiter of the common rail has been precisely adjusted at the factory. Therefore, any adjustment or replacement in the field must never be done. During its installation, the fuel pressure sensor deforms through tightening in order to ensure proper sealing with the common rail. If the fuel pressure sensor or the common rail must be replaced, they must be replaced together on an assembly basis because reusing them causes fuel leaks.